Okay, so today I'm going to talk about statistics of records. So what is a record? So I guess all of you have heard about Guinness World Records, right? Everybody knows Guinness World Record. Also, I guess many of you used to keep hearing, oh, Tendulkar broke this record, Tendulkar broke this record. Now probably you hear that Virat Kohli has broken this record, right? So what is a record? Huh? Extreme event till now, right? So it says that, okay, today in some place we had a record-breaking temperature. Means the temperature of that place on that day is higher than all previous days' temperature recorded, right? So record is an event. So if you have a time series, so you have these observations, and there's some kind of time. So there's a time sequence, right? There's a past, and when you break a record, it basically exceeds all previous values. It can be also small, like for example, lowest temperature. Sometimes you say, okay, it's the lowest temperature recorded in this place. So that's also a record, but it's like a lower record. Okay, so and is called a record. So this one, we call it upper record, let's say. Record if its value exceeds all previous objects. Okay, so this is you call a record. Okay, so why is this record interesting or important? So it basically tells you dynamically how this maximum is generated, right? So you have this maximum, and then next maximum will be somewhere else, right? So how the global maximum is reached? So it's like a dynamical process through which the global maximum is reached. Okay, so it's also important to describe things like this. In the Joachim Krug's lecture, he was talking about this fitness landscape and this population evolving in the fitness landscape, and it basically the population goes from fitter to fitter, right? So each time it goes from one fitness to a higher fitness, it breaks a record, right? So therefore, this evolution in this fitness landscape, you can also think of it like a record-breaking events, right? Basically, population gets fitter and fitter. Okay, and nowadays there are a lot of things about this climate change, global warming, and record is one of the way to tell people that, see, if somebody says that, okay, there is global warming, okay, probably people are not very distinct, but if you keep telling that, okay, there are this record-breaking temperature is happening, there's this lowest temperature, record-breaking lowest temperature happening, record-breaking highest temperature happening, and you look at the frequency of these records. So if you think that, okay, there are like a higher and higher, more and more these record-breaking events are happening, then you expect, if there is nothing like no global warming something, so then you think that, okay, this is one of the way to tell, say that, okay, there is something happening. Okay, so therefore this study of these records is an important subject, and what today I'm going to do is study of these records for IID random variables. Okay, so it's basically, so anytime you have something, some series, you have some record-breaking statistics. So this is the series you can compare with. Suppose nothing is happening, just all random variables are just random, right? And no global warming or nothing, it's just a random events. Okay, so what is the number of records you expect in a given time? And so this is your like the scale, right? And anytime you have some other statistic, you can compare with this scale, right? So therefore, this studying records for, or anything actually for IID random variables is very important, because that's like your point, with, this is your like a reference point with which you can compare things, right? So let me define it more precisely. So consider a IID random sequence x1, x2, xn. Right? So you consider a sequence like that, and in this sequence, there is always an arrow. Like you can think that, okay, this is some, let's say, temperature you have observed in some particular place every year in June or something like that. So there's an arrow. So it's like a time is increasing in that direction. Okay. So now, an entry in this sequence, let's say xn, that's the nth entry, it will be called a record. If xn is greater than xi for all I less than n, right? If this value is less than, greater than all previous values, then we'll call this a record. Okay. So now you can ask, so given this sequence of n elements, so each time you find an observation which is greater than the previous one, that's a record. So how many records occur in a given time? So your n is like time, right? It's like a discrete time. Okay. So this is the, so you can ask many different questions, but in this lecture, I'm just going to focus on one question, that's total number of records in a given duration, and in this case duration is just n, right? So because here this n is like time. Okay, so this is what you can observe. Okay, so let's first look at, so this is the total number of records, let's call it m, denoted by m. This is a random variable, right? So if you take one sequence, you will get this number something. If you take another sequence, you will get some other number. So it's a random variable. So it has a distribution. The question is, what is the distribution? So before finding the distribution, let's first find the mean. Okay, what is the mean? Let's find the mean. Okay. So let us define a variable in. So this is an indicator function. Okay, it takes two values 0 and 1. This is equal to 1 if xn is a record, or 0 otherwise. Right? So if xn is not record, then it's 0. Okay? So then the m is, you can just write, there are n observation, 1 to n, just I of n, right? So every time there's a record, it will give you 1. So this is just the number of records. Okay? So therefore, if you are just interested in the mean, this is just given by 1 to n, mean of this, because this is also a random variable, it takes value 0 and 1, and what is the mean of this object. Okay. So now we have to find out what is the probability that xn is a record in a given sequence. Right? So what is the probability? The probability that xn is a record, that means in equal to 1. See, what is this expected value of this in? Expected value of in is 1 is that value times the probability that in is equal to 1 plus 0 times the probability of the in equal to 0, but that's 0. So therefore it's just same as the probability that in equal to 1. Okay? So probability that in equal to 1 is equal to the probability that xn is a record. That means xn is greater than all previous values, right? So that's same as probability that xn is greater than x1, xn is greater than x2, xn is greater than xn minus 1, right? So this is what you have. So what is this probability? What is this probability? Probability that xn is greater than all. I have not told you what is the value of the record, right? I'm just asking that what is the probability that it's just greater than all previous values. So imagine that you are drawing this sequence. So this is your guy, right? So this is your x, this is your n. So let's say, so first one, okay, you just x1, you can just by convention, you can just call it a record. Okay, so this one, okay, is somewhere there, so that is low, so that's not a record, right? So next one value is supposed there, it's still not a record, right? Next one is there, so that's a record, right? This one is here, not a record. If this guy goes there, that's a record, right? So if something comes there, that's not a record. And so these observations are records, right? This one is record. So these are all low, then it goes there, this is a record, it stays there, this is a record, and then, so these are record guys. So now, probability that this is a record is the same as the probability that this is greater than all previous values. So what is that probability? That's equal to? Is okay? So this is 1 over n, right? So therefore this is equal to 1 over n. Therefore I have to compute the mean . 1 over n, right? So how does it go? So this is known, and this is something called harmonic number. Okay, so this guy is called BR, but we are just interested in large n. So if n is very large, how does this series behave? This n when it's very large, how does this series behave? So this basically large n almost goes like this. You can just replace by integral over n. So it just goes like log n. Okay. Yeah. Okay. Plus some. Okay. So this equal log n plus some gamma, so this is called Euler constant, and then plus order of 1 over n. Okay. Yeah. So this one is some number 0.577 something. Yeah. Okay. Some number. Okay. So therefore, the mean number of records with n grows like log n. So what does it mean? If something is growing like log n, so log n is a very slow function, right? So as n increases, it becomes harder and harder to make records, right? So if your observations are just IID, right, then the number of records increases like log n. So with time, it becomes harder and harder to make records, right? So now if you see that, okay, there is something more record-breaking events are happening, so therefore there must be something else, right? Not like this IID. Okay. So yeah.
Maybe also insist that this result that's 1 over n actually holds only for continuous.
Yeah. Okay. Yeah. So this one only holds for continuous distribution because this. See, if you have a discrete distribution, what happens actually? See, when I'm just writing down here, I'm assuming that there is no degeneracy, right? Yeah. So only for continuous distribution, this result holds actually. So whatever I'm going to talk about here, these are only for continuous distribution. Okay? Yeah. So now let's look at this thing. So you can also compute the variance in the same way. So if you want to compute the variance, what you need? So you'll do m square here, like suppose you want to compute the second moment, m square, that's the square of this one, and then you'll break it into two sum, then you'll need this correlation between Im and In, right? And then you need the joint probability distribution, right? So you can do it similar way, but instead of that, what I am going to do, I'm just actually going to derive the probability distribution of number of records itself, okay? So let me put it here, joint distribution. So let me define this object P of M, probability of having M records. So let's look at this picture. So this is, let's call R1, that's the first record, okay? This is R2, this is second record, this is R3, and so on, right? It will go up to capital N, okay? But a record number will be less than capital N or less than equal to capital N, okay? So now let's define one more variable, which is how long does it take to make the next record. So let's look at the duration and let's call it L1. So for example, here L1 is 1, 2, 3. So in this case, L1 is 3, right? So let's define this variable. So here again, L2, what is L2? L2 is 2, and so on. So let me, okay, so it will keep on going, and then you'll have some record. There are M records, so this will be some Rm somewhere there, right? But so Rm will happen at some time, and then you are measuring up to time n, right? Because this is your number of this thing, but there will be events even here, right? But those events will be basically lower than Rm, okay? So this last bit, let's call it Lm, right? So R1, L1, R2, L2, RT, LT, so on, okay? So these Li's, so L1, L2, Lm, This we call it ages. Okay, these are the ages of the records. So this is the basically that long it lives, the record lives. Right? Ages of the records. And this R1, R2, these guys, R1, R2, Rm. So this guy we call it values of the records, right? So by definition, these guys are R1 is less than R2 less than Rm, right? Because these are successive records, so it has to be in the increasing sequence. Okay? So let's consider the joint distribution of the whole thing. L1, L2, Lm, R1, R2, Rm, given n. N is the number of random variables here, right? So n is like the time. So given n, this is what you have. So this object is the joint distribution. So how do you write down the joint distribution? So this is equal to, first, basically we have to put all the conditions down, right? So what is this condition? It says that, okay, records are in the increasing sequence. So it says that, okay, theta of R2 minus R1, theta of R3 minus R2, theta of Rm minus R minus 1. Right, that's the condition which says that these are in this increasing order, okay, times, just multiply with this one. Now we have to draw these variables, right? So these variables are, let's say that we have drawn from some distribution P of x, which is continuous, okay? So then what is the probability of finding R1? Probability density, but this is like a density. So what is the probability of density of finding R1? So it's just P of R1, okay? Then what is the probability that next record is here? That means all the random variable in between is less than R1, right? So it says minus infinity to R1 Px dx. How many random variables are there in between? L1 minus 1, right? So L1 minus 1. Then this is a record, okay? So what is the probability of drawing that one? P of R2, right? We have already put the constraint that it's a record. Then all the other guys till R3 it's less than R2. So that's probability is minus infinity to R2 Px dx. How many of them are there? L2 minus 1 and so on, right? Then for the, so it will go all the way 1, 2, 2 all the way up to Rm. Then that Rm, so P of Rm, and then all these guys are less than this thing, minus infinity to Rm Px dx, and what is this number? So if I take this objects L to be from, see for this inside guys, what is the minimum value of L1? 1. It's just, you have to at least go to the next guy, right? Okay. So similarly, all these guys. So all these guys minimum value is L1, all this L1. Whatever this guy, Yeah, but that last guy could have been the last record, nth guy, and there is no more, right? But if we define this Lm takes value 1 to infinity, so then even here I can just put L of m minus 1, where all these guys takes value from 1 to infinity. Right? Is it clear? Okay. Is that all? Or something else now? Huh? Yeah, number capital N. So where is the number capital N comes here? So this summation of Li's is equal to capital M, right? Times delta of L1 plus L2 plus Lm is capital N, right? So this is the joint distribution of having M records with ages L1, L2 up to Lm, R1, R2, Rm. Right? This is a joint distribution, and if you have this joint distribution, now you can find out the number of records. But suppose we are not interested in these values of the records. Okay, so what do you do? So integrate over these values. So from this distribution, we want to find P of M, L1, L2, Lm, given N, right? So we have to integrate over all values of R. This is dr1, dr2, right? Minus infinity to plus infinity, minus infinity to, right? Because already this constant is there. So this integral limits I can just take it from minus infinity to plus infinity times that P. Okay, so these are different P, but I'm just putting the same P. P means just the probability, this thing. Okay? M, L1, L2, Lm, R1, R2, Rm, given N. Right? This is what we have to do. Okay.
Rm is greater than Rm minus 1 and so on. So why is the limit?
So this is there because when it is R2 is let's say less than R1 in that one, that will be 0, right? So it's there. So I can explicitly put the limits there by hand, or I can just put it from minus infinity plus infinity because it's there already in the probability distribution itself. Right? Yeah.
Here, aren't we already fixing n?
We are fixing M.
Aren't we given n and n?
No, it says that this is what is the probability that given n, there are M records. So you can just think of, let's say you have drawn some k realization of these sequences, right? And out of this k realization, how many realizations have M records, right? So you are putting down all those conditions basically, right? Yeah. Okay, so this one, so let's define a variable to do this integral. So let ui is minus infinity to ri dx dx, okay, for all ri, so you'll have a variable ui, okay. So what is dui? Is just E of ri dri, right? So let's define this variable because these are the objects which appear inside. So let's call these objects ui U1, U2, U3 like that. Then you see that dui is just this one. So therefore, that sum, that integral, you remember these guys are there. So this Pri times dri, that becomes du, and this becomes u, right? So this becomes an integral over u now, du1, du2, du m. Okay, so I'll put the limits later. And then these are just only these guys. No? So let me just write it here. du1, u1 to the power L1 minus 1, du2, u2 to the power L2 minus 1, du3, u3 to the power L3 minus 1, um to the power Lm minus 1, right? So that integral, when you substitute this guy, it will become this one.
This expression for probability.
Yes?
Where is the explicit
N.
M different? N.
Through these guys, there are m terms, right? There are m such terms. For each r, there is a term like that. So these guys come together, right? So there are m such combinations, right? So this is where m comes in. M, right?
My question was more like, now suppose I integrate over two of the variables.
Yeah.
I can get marginal.
Yeah.
I'm not able to understand how I would do that for it.
M. Yeah. So that's what we are going to do. So now we had this whole things. So I am integrating out this guy. Yeah. So I get the marginal of these guys. Now I'm going to integrate over these guys, and then I'll get the marginal of M. Okay? That's the joint distribution. It has all informations, and I'll integrate the other objects and get these things. Okay, so there are M terms. So the first, second, this is the mth term. Right? So this is what you have. Okay. So what is the limits of this one? Now u. R limits are from minus infinity to plus infinity. So when r is minus infinity, u is 0. When r is infinity, u is 1. Right? So these limits are from 0 to 1. Have you missed something? Yeah, so you have to put the step functions now. Right? So what is the step function now? These are step function in terms of r. Right? But this u is a monotonically increasing function of r. Right? So if r increases, u also increases. So therefore the step function in r becomes just a step function in u also. Right? So this times theta of u2 minus u1, theta of u3 minus u2, theta of m minus u m minus 1. Right? So this is what you have to do. Is there anything else? There's this delta function, right? Times this delta function L1 plus L2 minus. Okay? This is what you have. So these integrals you can actually carry out this integral, the whole integral. So this delta function is outside, right? Because for a fixed L1, L2, etc. So this delta function, like when you do the integral, this delta function doesn't come there, right? So these are just the polynomials, no, it's just the powers. So you can do this integral with the, when you're doing the m integral, right? Mth integral, so you'll need this guy, right? When you do the other one, you'll need that guy, so you can successively keep on doing this integral. Suppose without any limit, what is the integral? It's just u to the power m by lm, right? And then you have to take the limits, right? That limits will involve m minus 1, so that will come to that next integral. Again, you do the integral with this thing. So you can successively do this integral. So it's a homework. Check that this is equal to 1 over L1, L1 plus L2, L1 plus L2 plus L3, L1 plus L2 plus M. Okay, this guy, check that, check. You just do few of the terms and then you'll figure it out, right? That's for that integral, and then we have this guy, right? So it says delta of L1, L2, oh sorry, minus n, right? So that's the answer, okay? So you see that although, so it, yeah. So it's not in product form. If it was in product form, let's say 1 over L1, 1 over L2, then it would have looked like some independent this thing. But it's not independent, these edges are correlated. Okay? But I can actually look at another object, and it has actually a simpler one. So instead of these edges, I can actually look at the time at which successive record happens, right? Let's say this happens at time n1, so n1 is same as L1, right? This is n1, this time is n2, so n2 is, n1 is L1, n2 is L1 plus L2, and so on. So then you see that in terms of the times, if I given n1, n2, and n given n, so you see that that distribution becomes 1 over n1, 1 over n2, 1 over n3, so on. Last guy is just 1 over n because this is same as n, right? But of course there's a condition, so that just comes from the condition just all Li's are positive, right? That I did not put it explicitly, but there are this theta function, theta of L1, theta of L2, like that. So that becomes theta of n2 minus n1, theta of n3 minus n2, theta of nn minus n minus 1, right? So the
Just one thing. Delta function. Sum of Li L1 plus Lm. Exactly n minus 1.
No, this L1, Lm I have defined from taking value from 1 to infinity. Yeah, n minus 1, yeah, you're right, actually. Because, yeah, so this guy, if, yeah, that's true. Minus 1. Or I could have, yeah, so I could have, or what I could have done, I could have taken this Lm, so this, okay, so all the guys from L1 to m minus 1, they takes value from 1 to infinity. So this guy goes from 1 to infinity, but okay, which is bounded by n, right? But last guy, Lm, takes value from 0 to this thing. right? Because the last guy could have been the record, then there are no more distinct. So in that case, this that would have been distinct, but okay, let me just put it the same guy, 1 minus 1, and then let me just call it plus 1. Yeah, okay. Okay. Okay, so this is what we have. So now, if we want to find out the number of records, we have to also sum over this L, right? So LM also I have defined the same way, so all takes value from 1 to infinity, right? Yeah. No, it's N only. Because that first guy, I have defined excluding the first guy. See, L's are defined by this R1 is the first guy, then 1, 2, 3. For example, let's look at this object. Yeah, this is the example, let's say, right? In this case, yeah. So 1, 2, 3, 4, 5, 6, right? 3 plus 2, 5. Plus 1. L3 is equal to 1 by this definition. Because LM takes value from 1 to infinity. So in this case, since there are no more guys after this one, so LM is 1. Okay. In the other one, LM would have been 0, but then as we said that this guy would have gone from 0 to this thing, and that would have created a problem. Yeah. So so that one is fine. Is it okay? The way I have defined, see, this ages is just starting from the record, right? So this was my first record. So this guy basically waited 3 time step to break the record. Right? So it survives up to 3 time steps, okay? So therefore it age is 3. At the 3rd time step, it breaks the record, right? So that's why L1. LM is making the record here. It will survive at least 1 time step. The next record will be made at least the next time step or more, right? So therefore the LM is again go from 1 to infinity. Right? So then, yeah. Yeah, okay. So, yeah. So now, this, so thanks Abhishek, yeah. So this expression, actually, I could have written down directly without going through this derivation. So what does it say? This guy is a record. The last guy is a record. What is the probability that last guy is a record? So that's not the last guy. Whatever the mth guy, so that was the guy, that's the last guy. After that, there is no record, right? So what is the probability that that's a record? The probability that that guy is greater than all the previous guys, 1 over m, okay? But also, that's the probability that that's the global maximum. What is the probability that that's a global maximum? That's 1 over n. So that's this 1 over n comes. For the first guy, of course, this one. This is what is the probability that this is greater than all the previous one. That's 1 over n1. This guy is a record. What is the probability that this is greater than all the previous one? That's 1 over n2, and so on, right? And these are independent. So I could have actually written down this final formula directly, right? And then I could have, from this one, I could have written down this one, right? By in terms of, not in terms of N1, but in terms of L1. So I could have just gone from here to there directly. Okay. So now let's look at the distribution of the number of records. No, it's not coming from the delta function. This theta function, see, there are these theta functions here. Theta of L1, theta of L2, theta of Lm, right? Because this Lm takes value from 1 to infinity, these are positive guys. Right? So I did not put it explicitly here, right? Or in the expression, there are also theta function involving L's, right? Because L goes from 1 to infinity. I'm not putting down explicitly, right? It's just the condition that, okay, all the L's are positive. So there are these conditions L1, theta of L2, theta of Lm. So this condition is already there, right? Yeah.
Sir, again, the LM, if we say LM goes from 1 to 1 to 3,
yeah.
We are assuming that the RM record can't happen on the last step.
It can. So that's why I'm putting Lm minus 1, no? This will be 0, right? The last guy is the P of Rm, and there's nothing after that. So this will be 1 minus 1, 0. Right? Yeah. So if it goes from 0 to infinity, this would have been Lm. Yeah. So the way the age I'm defining is that if there's a record, if it is a last guy, age is 1 because at least 1 because it can happen only at the next step. Yeah.
The summation then won't be
Which one? Why?
because if it happens at last,
Yeah.
it will be just summation will be some more L1 and 2 plus L2 will be 5.
Yeah.
But there are 6 factorial.
3 plus 2 plus 1.
But you just said that
Lm takes from 1 to infinity. If it is a last guy, Lm is 1. Right? That's just by the convention. That's the definition I'm just taking. Okay? Yeah. Okay, so now let's try to find out the number of records. What is P of M of N? So what I have to do, I have to just sum over all these L's here. Right? So instead of summing over here, let's just go back to the original formula and we do it there itself. What is the original formula? There, and we'll sum it there. Yeah. You have something? This one, because that was the constraint, right? Huh? So therefore this becomes N. No, but no, this need not happen at the last step. It can happen anywhere. MF record can happen anywhere. Yeah. Because, like for example, this guy, this is the last record, right? This is N. This is the last record of the time. N. So this is N is basically all the way up to L of M minus 1. Right? Yeah, so there is a term where 1 over L1 N minus 1, the term is there. But there is also a term 1 over N, this one. This is what you said?
Yes.
Okay. Yeah. Okay. Yeah.
Short comment regarding solution. Would not have written down directly this. That assumes that all the INs are independent of each other.
Yeah. You have to prove it. Yeah, exactly. You have to prove it, but that takes another this thing. So you have to prove that. Yeah, exactly. Yeah, exactly. Because you have to prove that this guy actually you can write down this thing so that, yeah, okay. So now let's just look at this object. To look at this object, I need to take this formula and just sum over all L's, right? But instead of doing that, let's take this formula and use it from there. And let's also consider a generating function P of Mn z to the power n, where n goes from 0 to infinity, right? So I'm just including also n equal to 0 term. So n equal to 0 means basically P of 0, 0 will be 1. If there are no variables, then probability of having 0 record is 1. Basically, that's just the convention. Okay. So if we look at this object, so what do you get from this formula? What you get is, so this basically n equal to 0 to infinity, z to the power n, then L1 equal to 1 to infinity, L2 equal to 1 to infinity, Lm equal to 1 to infinity. So you just sum over all L, right? And then this P of M, L1, L2, Lm given n, right? And then I'm going to substitute this guy here. Okay. So what is this answer? So now you see that if you sum over n, that takes this delta function, right? So then it becomes L1 equal to 1 to infinity. What is this guy? All these integrals are there. Let me just put these integrals. Okay. So, okay. See this summing over n gives me these objects, this object here, okay, so that is equal to L1 equal to 1 to infinity, Lm equal to 1 to infinity, right? And then I have this integral 0 to 1 du1, u1 to the power L1 minus 1, and then 0 to 1 um to the, okay, dum to the power Lm minus 1, okay, you could, it's this, then this your, all these theta functions, and that z to the power m becomes z to the power L1 plus L2 plus Lm, right? It basically, so whenever you have this kind of delta function, what you do is basically you just take a generating function with respect to this variable, so it just leaves the delta function, right? So it basically decouples the, see, because of this delta function, it somehow keeps this sum together, right? You cannot do it this thing, so it just decouples it, okay? Now you see that, okay, u of L1 minus 1, there is a z of L1 minus 1, right? So what is this guys now? 0 to 1 du1. I can do the sum over L1. What is the sum over L1? There is a z. There is a z to the power L1 here, z to the power L1 here. So if I just keep a z outside, then z u1 to the power L1 minus 1, right? Sum over L1 from 1 to infinity, what is that sum? You like x to the power n, n goes from 0 to infinity, right? 1 over 1 minus x. So it's just 1 by 1 minus z u1, right? So similarly, I have this guy 0 to 1 du2 z by 1 minus ZU2 and so on, 0 to 1 du m z by 1 minus z u m, right? So this is what you have, and of course you have this theta functions of u1s, right? 1 minute. Right? Yeah. Okay. This is okay? A little bit bigger than that. Okay, fine. Yeah. So I'm going to. So this is what you have. I have to anyway go to that other side now. That's a big problem. Okay. So now let's look at this thing here and let's go to that other side. So what is that integral? You have these integrals with the, you have those multiple integrals, and then you have these theta functions, right? So this you will in fact encounter in various other problems. So what do you do? See, again, you cannot, because of these theta functions, you cannot do these integrals independently, right? Because there's this constraint. Of course, you can put this thing and you can actually carry out the integral. It's not that you cannot do the integrals, right? You have to just put the limits according to this thing, and you can, because this is what is the integral of this guy? It's some log of something, right? Log of this down guy, right? But there's another trick. The trick is that this u1, u2, these are all dummy variables, right? These are just integral variables, dummy variables. Huh? Integrands are same, right? I could have written, instead of this, I could have just written du1, du2, dum, then 1 over this one, 1 over this one, 1 over this one. So integrands are of the same form, and u's are dummy variable. So if I make a change of variable, any permutations of u, ui, u1, u2 after this portion doesn't change, right? Under any permutations of u. Let's call u1 to u2, u2 to u1. It remains same. What will change is this guy. So this guy changes under permutation. This guy doesn't change under permutation. But any permutation will give me the same answer, because these are just the dummy variable, and if I make a change of variable in the integral, the answer doesn't change. Right? So if I have an integral dx, dy, x I call it z1 and y I call it u or something, it's just a change of variable. It doesn't change the answer of the integral. Right? So therefore, all n factorial permutations of, there are how many? M variables. So there are m factorial permutations of these u's. So all these m factorial permutations will give you the same answer. So therefore, I can write down all the m factorial permutations and add them up. So that will be m factorial times whatever n equal to, okay, let me just write it here. That's why since I'm going, because each guys are same, so m factorial times n equal to 0 to infinity p mn z to the power n is, this is the guy, this one, 0 to 1 du1 z over 1 minus zu1, 0 to 1 du2 z over 1 minus zu2, 0 to 1 du m z over 1 minus z u m. I just remembered that I was supposed to write bigger. Then these theta functions, right, coming from each permutation. So this guy is same. So I can, for each permutation, I can take out this side. And now I have this theta function which is different for each permutation. So let's just put a something, I don't know what to call it. Let's just call it some theta p. Just a p represents just one permutation of this thing, right? So this is basically theta of p sum over all permutations, right? Sum over all permutations. So this represents, right? So it will be different at each time because these theta functions will be arranged in this variable inside the theta function will be in different orders, right? For example, just think of one permutation where I have only changed u1 and u2. Nothing else I have changed. This would have been then theta of u1 minus u2, and this will be theta of u3 minus u1. The rest will be same, right? But now, if I sum over all these permutations, what do I get? 1, right? Because whatever your permutation, there will be one condition, theta function condition, that will be always satisfied, right? So therefore, this is equal to 1. Now you see that this actually has become very simple. Now there is no constraint, it's unconstrained integrals, right? This integral I can do separately, this integral I can do separately, this integral I can do separately, and these are all same integrals, right? Because these are just the u, just a dummy variable. So therefore what I have is that n equal to 0 to infinity p mn z to the power n is 1 over m factorial, this one. And what is the value of that integral? Minus log of 1 minus z to the power m, right? Because this minus dd u of log of is z by 1 minus ZU, right? So this is what, then I can just do the integral. Okay, so this is what you have. So very good. So you have the, basically the generating function. So whenever you multiply to it, so these are called generating functions. So you have the generating function with respect to n, you have the answer. So now to get to p of mn, of course you have to invert it, right? How do you invert it, these generating functions? What is the p of mn? What is this? 1 over 2 pi I dz by z to the power n plus 1, this guy, the generating function. So it is 1 over m factorial log of 1 minus z to the power m, right? Okay, but let's not do this way, and let's do one more thing. Let's just take a generating function now with respect to m also, right? Because this guy looks something familiar, no? Something to the power m by m factorial. It's just the coefficients of x to the power m in the expansion of exponential, right? So therefore, if I take a generating function with respect to m also now, m equal to 0 to infinity, let's call it w, this variable, n equal to 0 to infinity, p m n z to the power n. What is that? Now I am summing over m from 0 to infinity, just that exponential of minus log of, there's a w here, right? So I'm multiplying by w to the power m and summing. So exponential of minus w log of 1 minus z. What is that? W I can take it there, right? So it's just 1 over 1 minus z to the power w. Okay? Now this expansion all of you know. What is this expansion? One plus wz plus w plus 1 by factorial 2 z square, so on, right? It's a infinite series, right? So therefore, if I just compare the coefficient of z to the power n from there, what do I get? So if I compare the coefficients of z to the power n, then I have only infinity w to the power m p of m n. What is this? Is just the coefficient of z to the power n term. Coefficient of z to the power n is w plus 1 all the way up to w plus n minus 1 divided by n factorial, right? The first term is w, second term is w into w plus 1, third term is w plus 1, w plus 2, so it goes up to n minus 1, right? So what we have is basically the generating function of the number of records for a given n, right? This one, of course, you have to now invert it to find the p of mn the same way, right? Here we are doing that. Instead of that, it will be just a contour integral of this one, and you have to do that, okay? But before that, let's just find the answer, okay? So let me just give a, okay, so anytime you have something, what you should check is the first the normalization. How do we check the normalization from this one? Normalization means what? 0 to infinity p of fn, it should be 1. Is it 1? If I put w equal to 1, you see that that's like 1, 2 up to n, so that's n factorial cancels, that's equal to 1. You can also compute the mean, check the mean again, homework. What is the mean? If you multiply with, take a derivative with respect to w of this object and then put w equal to 1, what will you get on the left hand side? If you take a derivative, it will come m w divided by m minus 1, right? Then put w equal to 1. So that will give you the mean. Do it also on the right hand side and check that you get the whatever we have got it before, right? Also calculate the variance and see what you get, okay? Okay. So you can also look at the statistics of this else, but okay, let's not do it today. Okay, so now what I'm going to do, so this guy is also a generating function of something we already know. That's called Starling numbers. right? Have you heard about Starling numbers? Okay. So this is a known generating function. In fact, this generating function is, okay, so that 1 over n factorial is already there, that top guys, okay. So this is a generating function of some object, let me just define, equal to 1 to infinity. So you see that now, in this case, for a given n, which is non-zero, the lowest order comes with w, right? Therefore, the p of 0 n is 0 always, right? Because by definition, we say the first one is record, right? So it just always comes from there. So this basically m basically comes from 1 to infinity. The 0 term is not there. And this is written something like that. I'll explain what this w to the power n. Okay. So this box guy, so this one is called Einstein Starling number of first kind. Okay, so I'll tell you what is this object. Okay. So therefore, this P of m given n is basically 1 over n factorial, and just combining the coefficients of this w to the power m times n m, right? So I'm going to tell you what is this object, but it's some known object, okay? It's called Starling numbers, and if you sum over m equal to 1 to n, this object, this is factorial n, so therefore again your probability is normalized, okay? And then you can actually look at the large n behavior of this object, okay? So from which you can show that P of mn goes like 1 over square root of 2 pi log n okay. So for large n, typical number of records is like log n, that we have already seen when we computed the mean with
square.
right? So typical number of records goes like log n. So we already saw that for large n, the mean goes like log n. The variance is also log n, and its fluctuations are Gaussian around log n for its large m and n. Okay. So now let's see what is this object Starling numbers. Okay. So this comes from permutations of numbers. Okay. So let's look at permutation of numbers, and let's look at the case when n equal to 3, permutation of 3 numbers. Okay, so these 3 numbers 1, 2, and 3. Let's call 1, 2, and 3. Okay, any 3 objects, permutation of 3 objects. Okay, so how many permutations are there? 3 factorial, so 6. So what are the permutations? 1, 2, 3. Okay, let me just write down the things. So 1, 2, 3. So it's basically the same permutation. One is just 1, 2, 3. Okay. One is 1, 2, 3. 1, 3, 2. So that's the lower line is the permutation of the object basically 1, 2, 3. So it's just the same one. So this is one permutation. There's this another permutation which is 1, 2, 3, 2, 1, 3. So this is this one. Then 1, 2, 3, 2, 3, 1. And then this permutation 1, 2, 3. Permutation 1, 3 is 3, 1, 2. This is another permutation. And this is 1, 2, 3, 3, 2, 1. This is another permutation. Okay. So these are the 6 permutations. Permutation of 1, 2, 3 is 1, 2, 3, 2, 3, 1, 1, 3, 2, 3, 1, 2, 2, 1, 3, and 3, 2, 1. Right? These are the 6 permutations. Okay. So permutations also you can represent in terms of something called cycles. Right? For example, this one, what happened is 1 goes to 1, 2 goes to 2, 3 goes to 3. So this you can write 1, 2, 3. So it's just like a cycle of length 1. Right? This permutation, on the other hand, 1 goes to 2, 2 goes to 3, 3 goes to 1. Right? So either I can give you this one or I can give you this one, it represents the same. Right? I can represent in terms of this one or this one. So this one I will write as 1, 1, 2, 3. Okay? This is just one cycle of length 3. This one, 1 goes to 1, 2 goes to 3, 3 goes to 2. So it's 1 and 2, 3. Right? So this is cycle of 1 and cycle of 2. So given this one, I can just write back that one. Okay. Similarly, this one, 1 goes to 3, 3 goes to 2, 1 goes to 3, 3 goes to 2, 2 goes to 1. So it's 1, 3, 2. Right? This one, can somebody tell me? 1 goes to 2, 2 goes to 1, so 1, 2, and 3 is alone, 3. This one, somebody tell me? 1 goes to 3, 3 goes to 1, and 2 remain. So this 2 and 1, 3. Right? So how many cycles are here? There are 3 cycles. This each bracket corresponds to 1 cycle. Right? So let me just represent cycle by m. So this is 1 cycle. So m equal to 1, 3 cycle, m equal to 3. Okay? So it says basically 3 cycles here, 1 here, 2 cycles, 2 brackets there, right? 2 cycles here, 1 here, 2 here, m equal to 2. So how many cycles are there of length? How many permutations are there where there is only 1 cycle? This one, and one, this one, 2. So number of permutations having 1 cycle is 2. So that's called the Stirling number. The Stirling number, and m is basically the number of distinct cycles with number of exactly m distinct cycles for permutation of n objects, right? So that's the definition. So in this case, we saw that 3, 1 is what? 2, because this is 1 and 1 here. What is 3, 2? How many has 2 cycles? 1, 2, 3, right? This is equal to 3. And how many has 3 cycles? How many has 3 cycles? That's only the first one, right? So that's 1, okay? So these are the Stirling numbers basically, okay? These are called Stirling numbers. So it says that if you have n objects, and then it basically says that how many permutations are there where there are exactly m cycles, okay? Now imagine that you have each permutation you just put it in a box. So you have a box and like, okay, each permutation you put it in a bag and then put it inside the box, okay? There are n factorial objects in the box, okay? Okay? So therefore, each has equal number, 1, right? So now if you randomly pick up 1, so what is the probability that you find a permutation with exactly m cycles? This probability will be exactly this one because you are just dividing by factorial n, right? So therefore, this P of mn for the permutation problem, it says that, so these are called random permutations. Basically, if you just randomly pick up one permutation out of this n factorial, finding a permutation with having exactly m distinct cycles, okay? So this is called a permutation this thing. So let me just, I did not tell you how actually why this is equal to that, right? I've just told you that this is given by that and what is this one, okay? So let me just see, I think this 2 minutes and I think 5 minutes or 7 minutes I have. So let me actually show that for permutations of the probability of having exactly m cycles for a permutation of object n is given by actually this object, right? This I have not shown, okay? So let me just do this quickly. Okay, so let me define this probability P of K1, K2, Kn, there are n objects, okay? So this is a probability or let me define this n or number K1, K2, Kn for a given n. So let me define, this is the number of permutations out of n factorial. These are the number of permutations having K1 cycles of size 1. Okay, now I'm actually going details into the cycles. See here, I'm just only telling how many cycles are there. But what is the length of the cycle? This is a cycle of length 3. This is a cycle of length 1. This is a cycle of length 2. So for example, here you have 3 cycles are there of length 1. So K1 is 3. In this case, you have 1 cycle of length 1 and 1 cycle of length 2. So K1 is 1, K2 is 1, right? So K2 cycles of size 2, K3 cycles of size 3, and so on. kn cycles of size n. Okay, let me just define this object. Okay, and now let me just represent each cycles irrespective of this by a cycle of length 1 by a dot, cycle of length 2 by a dimer, cycle of length 3 by a trimer, and so on, right? So then each permutation I can represent in terms of the cycles okay. So there will be cycle of length 1, how many are there? K1 are there, right? For example, in this, the first example, K1 equal to 3 and all the K's are 0. Then there will be cycles of length 2 and so on. K2 are there, right? Then there will be cycles of length n and there are kn there and so on. Okay, the whole permutation I can represent in terms of the cycles. Okay, there will be some numbers here. Okay, you can represent these cycles. Now I have to find out basically how many permutations are there where there is a given k1, k2, kn, so on. Okay, out of n factorial permutations. Okay, so how many are there? There are n factorial of them. Okay, so I have to find out this guy. So this is equal to, there are n factorial of there. There's a total number of permutations. Now there are some restriction. I have to basically reduce those numbers, right? Okay, so how do I reduce this number? Now if I go to within any k cycles, right? If I permute them within that, if I take a bracket here and put it there, that represents the same permutation, right? Because the way I written, usually I just write it from in the increasing order. So it represents the same permutation. So it's not going to change this thing, right? So that representation basically I have to reduce from this factorial n. So therefore there will be kn factorial, because for n such brackets I can do kn factorial ways, right? And n of course goes from 1 to n. So this is the within the brackets. This is among the brackets within a given group. Now I can go within a bracket, right? And of course if I permute, that corresponds to a different permutation, but if I permute it cyclically, like for example, if I, instead of writing this is 1, 3, 2, I could have written 2, 3, 1, that represent the same permutation. So any cyclic permutation within that group remains your cycle representation unchanged. So for an object of there are n elements, how many cyclic permutations are there? N, right? Because it's just what are, let's say 1, 2, 3. I can write 2, 3, 1, 3, 1, 2. If I have 4, it's just basically I'm just shifting one element, and it's like a periodic boundary condition, right? I'm just shifting by one element. So there are n there. So I have to divide by n for each groups. There are kn groups, so to the power kn, right? So this is this object n, right? So therefore I can again, like the way I define this probability distribution over these permutations, random permutations, I can define a P of having k1, k2, kn given n. This is just n divided by n factorial, and this is just 1 over, there is something here, okay? Is it done, the top one? No. there is some constraints, no? 1 to n, kn factorial, n to the power kn. This kn, k's, can they take any values? So there's summation n kn has to be equal to n. Right? Because these are the total number of elements. Right? So therefore this one is delta of summation n kn 1 to n minus n. Okay? So this is what you get. And then, okay, homework, check the normalization, summing over all k's, you get this thing. Now what is this object m? It's just the total number of cycles, irrespective of their size, right? So therefore number of cycles is just sum over k is just the k1 plus k2 kn. This is just the number of cycles, right? Then we want probability distribution of k given n, right? So you can again take a generating function w to the power k goes from 0 to infinity. So if you take a generating function, this is by definition expectation value of w to the power k, right? But this is by definition again k1 plus k2 plus kn, right? But we already have the distribution of this k1, k2, kn, which is given by that. So therefore, this is sum over all k, k1 equal to 0 to infinity, k2 equal to 0 to infinity, kn equal to 0 to infinity, right? This guy, so product over n equal to 1 to infinity, 1 to n, delta of n kn minus n, then w to the power k. So this one basically I can write w by n to the power kn factorial, right? This product is over product is over n. So as we said before that, okay, anytime you have this delta function, what do? You take a generating function with respect to that delta function, right? Then you see that n equal to 0 to infinity, wk, which is basically this one. So that just leaves this delta function and replaces wk z to the power k n, okay? That replaces this delta function, and instead of z, it will just put this guy, right? So what do we have? So you have this k1 equal to 0 to infinity, k2 equal to 0 to infinity. Now it's a infinite sum, right? Earlier this was up to kn, but now I have sum over all n, so it's an infinite sum. Okay, and then I have that guy. For each n, I have this, okay, this is an infinite sum now, n equal to 1 to infinity. What do we have? 1 by kn factorial, w to the power kn, okay, so there is this z to the power n kn divided by n kn, this one, right? Is it okay? So now I just each guy I can just sum over this k. So what do we have? If we just sum over k for each guy, so this means, so you have an infinite product n equal to 1 to infinity. This sum you can do, right? Now I am just putting the sum inside, taking the this thing outside, and for each k I am just summing over k from 0 to infinity. What is that sum? Something to the power something divided by factorial, that's exponential again, right? So you have exponential of, what is that? Z to the power n by n. And where is the w gone? There is a w here also, no? Z to the power n, w by n. This is what you have, right? So, as you know, that product of exponential is sum, if you take it there. So, you know this sum? What is that sum? What is the sum? Sum over x to the power n divided by n. Minus, okay, w is there, log of 1 minus z. And this is equal to 1 by 1 minus z to the power w. It's the same generating function we got for the records, right? So therefore I proven that the whatever the Stirling number you get for the permutation, Stirling number is just the definition, but this is basically the generating function of the Stirling number is given by that, and that's the same generating function for the number of records basically, right? So then I proven that, yeah. So basically the statistics of number of records for IID random variable only for the number of records is same as that of number of distinct cycles in the random permutation problem, right? So it says that if we just randomly pick up a permutation, what is the probability of having distinctly m cycles? That's same as this number of records basically. Okay, I think I've taken a little bit